Lesson 3.3, Kinematics of Rotational Motion. Rotational motion describes spinning motion. When we use rotational motion, theta is like the x. X equals r, theta is position. So theta is how many angles it is rotated. X is the distance it is gone. Angular velocity is like linear velocity. Angular velocity is our change in angle over time. And linear velocity is the radius times the angular velocity. Alpha, which is angular acceleration, is like your regular acceleration. Angular acceleration is your change in angular velocity over time, the rate of change in angular velocity over time. And our tangential acceleration is r times the angular acceleration. Oh, so you see there's a pattern. The linear, the tangential, is r times the angular quantity. For the angular quantity, counterclockwise is positive, clockwise is negative. So there are two components to acceleration. We have centripetal acceleration, which is towards the center. And centripetal acceleration changes direction only since it's perpendicular to the velocity. Centripetal acceleration will only change the direction, which is v squared over r. Tangential or linear acceleration is tangent to the circle. And it changes the speed only since it's parallel to the v. And tangential acceleration is r times the angular acceleration. When you combine those two, you get the total acceleration of the object. So the equations of kinematics for rotational motion are the same as for linear motion. We have your position equals your average velocity times time. Distance equals velocity times time. Velocity is the acceleration times time plus the initial velocity. Position is 1/2 acceleration times time squared plus the initial velocity times time plus your initial position. And that one's also true. So our reasoning strategy. First, examine the situation to determine if rotational motion is involved. And then identify the unknowns. Drawings could be useful. Identify the knowns. Know the unknowns. Pick an appropriate equation based on the knowns and unknowns. Substitute those values into the equation and solve. And check and see if your answer is reasonable. A figure skater is spinning at 0.5 revolutions per second, and then pulls her arms in and increases her speed to 10 revolutions per second in 1.5 seconds. What is her angular acceleration? Well, the first thing we need to do is convert the revolutions per second to radians per second. And 1 revolution is 2 pi radians. So half a revolution per second would be pi radians per second. And 10 revolutions per second. 1 revolution is 2 pi radians, would be 20 pi radians per second. And so this is our initial angular velocity. This is our final angular velocity. And our time is 1.5 seconds. And we're looking for angular acceleration. Well, we could use that one. So our final velocity equals the acceleration times time plus the initial velocity. Subtract the pi radians per second will give us 19 pi radians per second. Divide by the 1.5 seconds, and you should get 39.8 radians per second squared. Watch what happens when this figure skater is spinning and accelerates angularly. A ceiling fan has 4 evenly spaced blades of negligible width. As you are putting on your shirt, you raise your hand. It brushes a blade and then is hit by the next blade. The blades are rotating at 4 revolutions per second and stops in 0.1 seconds as it hits your hand. What angular displacement did the fan move after it hit your hand? Well, we know our initial velocity is 4 revolutions per second. Convert that to radians. So it'll be 8 pi radians per second. And our time is 0.01 seconds. And we want displacement. Okay. So maybe we could use that. Oops. 2. So this is position is average velocity times time, but the average is adding up the initial and final and dividing by 2. So it stops, so our final velocity is 0. The initial is 8 pi, and our time is 0.01 seconds. Which is 0.126 radians. If you wanted that in degrees, we could convert to degrees. There are pi radians in 180 degrees. So times 180 and divide by pi, and that would be 7.2 degrees.